Good morning, everybody. Welcome to day 3 on week 5 of the semester. Today in class, we are going over the topics of chapter 14. So in chapter 14 will be the last chapter where we talk about organic chemistry. In this chapter, we are going to talk about the last 4 functional groups that we mentioned in the beginning of our discussions in organic chemistry. So now we are going to focus on specifically carboxylic acids, esters, amines, and lastly, amides. The first functional group that we are going to be focusing on is going to be carboxylic acids. And carboxylic acids, as we learned earlier in chapter 11, it is a functional group that it is composed of a carbonyl functionality that next to it is going to be a hydroxyl group. Now, understand that when we have a carbonyl and it's next to a hydroxyl group, that whole group is known as a carboxyl group. So carbonyl plus hydroxyl equals carboxyl. Now, understand that carboxylic acids are actually produced in nature. They're also synthesized in the laboratory. Put a 1 in the chat if you yourself or you know somebody that has been stung by a fire ant. It kind of hurts a little bit, huh? Anybody? Oh, only 1? I feel your pain. I also been stung by a fire ant. So when the ant is actually stinging you, when it bites, what it deposits on the skin is actually a carboxylic acid known as formic acid. Oh no, yeah, the bee sting, that is a different set of chemical compounds. Now, when it comes to formic acid, it is what actually is placed on our skin. Again, back in chapter 10, learned the properties for acids, and carboxylic acids are actually weak acids. Now, formic acid is going to be the common name for the carboxylic acid that you see there. Formic acid is another word that we can use for the compound called methanoic acid. And we're going to learn how to name these compounds. Now, other compounds that you may be familiar with in terms of taste is vinegar. And when it comes to vinegar, what gives that sour taste in vinegar, and similar to many of the carboxylic acids that are out there that you can consume, you can see that ethanoic acid, which is the same thing as acetic acid. Acetic acid is the common name for this compound, is what gives that sour taste to the ethanoic acid. Now, as we learn in chapter 10, one of the physical properties of acids is the sour taste. And because carboxylic acids are weak acids, that is also going to be a feature that is going to be common to carboxylic acids. So as we have done throughout our discussions in organic chemistry, we are now going to focus on how to go from structure to name and from name to structure in some cases. Just make sure that you guys practice in the worksheet going from structure to name and from name to structure. In class, I'm only going to be focusing on going over problems from mostly going from structure to name. So make sure that you practice. I will be posting most likely by tomorrow the answer keys for worksheet for chapter 12, 13, and 14. So let's now explore how do we name carboxylic acids. So as we have done throughout our discussions in organic chemistry, carboxylic acids is not any different when it comes to rule number 1, which is identifying the longest carbon chain that we have in our structure. Now, when it comes to carboxylic acid, that carbon chain needs to contain the carboxyl group. Now, we write the name of the alkane, okay, of our parent chain. At the end, we're going to replace the E in the alkane name by oic acid. So that's how we learn, how we name, how to name carboxylic acids. We end in oic acid. Now, the second rule is very similar to what we have done throughout. You're going to then give the location and the name of each of the substituents on the main chain, taking into account that the carboxyl carbon is going to be carbon 1. Similar to what we saw in aldehydes, carbon number 1, you don't need to specify 1, whatever carboxylic acid, because carbon number 1 is always going to be the carboxyl carbon. So remember, you cannot forget in the functional groups that we're naming throughout chapter 14, those rules for whenever you have one or multiple substituents. So let's get started with the skeletal structure that we have on the top. Let's put in the chat, how many carbons in the longest carbon chain? Excellent. Since we have 6 carbons, and let me number them, 1, 2, 3, 4, 5, 6. That means that the alkane name for this is going to be hexane. We delete the E and we write oic acid. So the parent chain name is going to be hexanoic acid. Here we have 2 substituents, and I know you guys are pros at this. What would be location and name of the substituents in this carboxylic acid? Let's put it in the chat. Great job, Yesenia. For chloro 3-methyl hexanoic acid. Okay. Let's move on to the second example that we have here. So far, when it comes to aromatics, you guys have learned about toluene, aniline, phenol, and benzaldehyde. I want to add one more member to that crew of aromatic compounds that have a particular common name that can be utilized, and that is going to be the name of your parent chain. So in this molecule, whenever we have a carboxyl group added to benzene, that whole group is known as benzoic acid. And as we have learned before, in the case of aniline, toluene, phenol, benzaldehyde, and now benzoic acid, carbon number 1 is going to be the carbon in the benzene ring that is going to be holding the motif that gives that common name to your benzene ring. So carbon number 1 here is going to be specifically this carbon atom. Now we have 2 substituents in the system, okay? We have the methyl and we have the ethyl group. So taking into account that is carbon number 1. Then we need to select, because of the substituents that we have here, if we're going clockwise or counterclockwise to make sure that the rest of the substituents have the lowest number, okay? In this case, if I go counterclockwise, then my ethyl gets a 3 and my methyl gets a 5. So that would be 1, sorry, and my methyl will get a 6. So it's going to be 1, 3, and 6. If I go in the clockwise direction, this is going to be a 2, 3, 4, 5, 6. Then my substituents get a 2 and a 5. That is going to be lower number than having a 3 and a 6. So this is the correct arrangement in terms of the numbering of the cyclic system. Taking that into consideration, let's put in the chat what are going to be locations and names for the substituents in this benzoic acid. Great job, Gia. That's how it is. Great job, Jasenia. It's going to be 5 ethyl, 2 methyl, benzoic acid. Okay. Let's do some practice. Given a structure, let's write what is going to be the IUPAC name for the following carboxylic acids. So I'm going to give you guys 3 minutes to write what are the IUPAC names for the following carboxylic acids. Let's get started. The first molecule, the longest carbon chain, has 1, 2, 3, 4, 5 carbon atoms. So this means that when it comes to the name of a functional group, this is going to be pentanoic acid. We have 2 substituents, 1 on 3 and 1 on 2. The 3-bromo goes first, followed by the 2-methyl. Put a 1 in the chat if you got the correct answer. Excellent. Great job practicing. Second one. Here, we have a benzoic acid. So that means that carbon number 1 is where we have our carboxyl group. In this aromatic structure, we have to number this clockwise. 2, 3, 4, 5, 6, to give that second substituent the lowest number. So when it comes to the name of that second molecule, this is 2-ethyl benzoic acid. Put a 2 in the chat if you got the correct answer. Great job, April. Last one. We have 1 carbon atoms, 2, 3, 4, 5, 6, 7. So what is the name of the parent chain here if we have 7 carbons and it is a carboxylic acid? Heptanoic acid. On carbon 3, we have a substituent, the one that looks like a Y. What is the name of the substituent that in skeletal form looks like a Y? Excellent. By now, you guys should know. That's isopropyl. So this is 3-isopropyl heptanoic acid. Questions going from structure to name when it comes to carboxylic acids. Since there are no questions, then let's move on to the next topic, which is going to be the properties of carboxylic acids. So when it comes to carboxylic acids, the first thing that we need to mention is polarity. When it comes to polarity, let's understand that as a carboxylic acid, because your carbon atom is actually bonded to 2 oxygens, and that oxygen in turn, the single bond oxygen specifically, is bonded to a hydrogen, there's actually 2 polar bonds in the system, okay? One is going to be the carbon double bond to oxygen in the carbonyl. The other one is going to be the oxygen-hydrogen bond that we have in the hydroxyl group as part of our carboxyl motif. So having these 2 polar bonds, polar covalent bonds, I should say, in this structure actually gives carboxylic acids very specific properties. One of them is that if you have a molecule of carboxylic acid, and I'm just going to draw another one to illustrate the process. One of the things that can happen is hydrogen bonding. In the hydrogen bonding events that are going to happen between 2 carboxylic acid molecules, the partial negative of the oxygen in the carbonyl of 1 is going to hydrogen bond, as you can see, similarly with the hydrogen of the OH in the neighbor. So as you can see, we can have the oxygen in the carbonyl of one molecule interact with the hydrogen that is single bonded to the oxygen in one molecule and vice versa. So having this property actually means that whenever we find carboxylic acids, they form what are called dimers in organic chemistry. You will find them in pairs like this, okay? So because of that, that is going to have effects on the boiling point and the melting point of these structures. Also, solubility in water, which is the next thing that we're going to mention. So as you can imagine, carboxylic acids are going to be soluble in water. And look at all the hydrogen bonding events that can happen between them. Since your oxygen atom in your carboxylic acid actually has two sets of lone pairs, which I'm just drawing them in. That's why it can actually have two hydrogen bonds with water molecules specifically. Now, because carboxylic acids themselves also have an OH group, then understand that the hydrogen in the carboxylic acid can also form a hydrogen bond with the oxygen in the water. And that's what we see illustrated specifically here. That the oxygen atom in the water can hydrogen bond with the hydrogen atom that is attached to the single bond oxygen in your carboxylic acid. Now, the oxygen atom that is single bonded to the carbonyl group in the carboxylic acid also has two lone pairs. And as you can see, those lone pairs, that electronegative atom that oxygen is, can hydrogen bond with water molecules. So you can observe that the amount of hydrogen bonding events that can happen specifically for carboxylic acids is higher than other functional groups that we have explored so far. Now, understand that there is a limit to the number of carbon atoms that you can have in a carboxylic acid in order for those carboxylic acids to be soluble in water. Carboxylic acids that have 1 to 4 carbon atoms are very soluble in water. Now, the minute that you have 5 carbon atoms or more, then understand that the solubility starts decreasing to the point that the more carbon atoms that you have in your molecule, then your carboxylic acid is going to be insoluble in water, okay? So the rule of thumb for carboxylic acids is anywhere between 1 to 4, very soluble. Then at 5 carbon atom solubility starts decreasing, okay? Now, as we have seen, there's a reason why these molecules are called carboxylic acids. And understand that since they are acids, they have a particular role that we discussed back in chapter 10. If something is considered an acid, is it going to donate protons or accept protons? So is it going to donate protons or accept protons? What do acids do? Excellent. It's going to donate a proton. So whenever we have a carboxylic acid in the presence of water, understand that since carboxylic acids are weak acids, it's going to donate protons to the base that it is paired with. And in the case of water, when water acts as a base, and remember that that carboxylic acid is going to be a weak acid, then what we see is that in this reaction, we are going to form what is called a carboxylate ion. In turn, when water acts as the base, then we're going to form its conjugate acid, which is the hydronium ion. Now, understand that this reaction between carboxylic acids and water, it is actually reversible. Because when it comes to identifying, okay, does it look more like forming that carboxylate ion, or specifically looking at carboxylic acid, this reaction is in equilibrium. The equilibrium actually is more towards the reactants because hydronium as a conjugate acid actually is more willing than a carboxylic acid to donate protons. So when it comes to this equilibrium, we're mostly going to have carboxylic acid in water. Now, one of the things that I want to specify, because it's not discussed in detail when it comes to the textbook, is going to be the naming of that carboxylate ion. When we are naming a carboxylate ion, understand that we are going to take our carboxylic acid name, and we're going to replace the ic acid in your carboxylic acid name with the suffix ATE. So when we look closely here, we have ethanoic acid. The carboxylate ion that comes from ethanoic acid, it is called ethanoate. Because again, we remove the ic acid and we put ATE at the end of it. So let's do an example. What about if I have butanoic acid? What is going to be the name of its carboxylate ion? So if we have butanoic acid, what's going to be the name of its carboxylate ion? We're missing an O in the name, but that's a good attempt. Is butanoate ion. Now, why is it that carboxylic acids are able to donate these protons and form these carboxylate ions? Well, when we look at the carboxylate ion, one of the things that can occur is that that negative charge on the oxygen can actually be shared into the carbon atom that it is next to. And then the other oxygen atom can become negatively charged. So by what I mean by that is that we can actually draw this also in this manner. And understand that basically what we are proposing here is two correct Lewis structures for that carboxylate ion. This has a name. These are called resonance structures. And these resonance structures, again, show you that electron density that it is shared in that carboxyl area of my molecule, and that actually provides stability to the ion that has been formed. Let's now move on to talk about reactions, okay, with carboxylic acids. And this is going to be the first reaction that we discussed, which is the neutralization of a carboxylic acid, okay? Now, neutralization is not a reaction that is new. This reaction we actually learned in chapter 10. So if you recall from chapter 10, a neutralization reaction is where we have an acid plus a base. And when they combine, we form salt. And remember that salt is going to be an ionic compound. And you make water. In essence, a neutralization reaction is going to be a double replacement reaction, okay? In which there's going to be an exchange of ions, if you want to think about it there. But at its base, it's just an acid-base reaction, okay? In which there's going to be an exchange of protons. So you can visualize it in both ways. The more appropriate way will be, this is an acid-base reaction, okay? So what happens when we neutralize a carboxylic acid? Well, the neutralization, the acid is going to be the carboxylic acid that you're working with. The base is going to be a strong base. And as you can see in the example here, it could be sodium hydroxide, it could be potassium hydroxide, it could even be lithium hydroxide, but it's going to be a strong base. So overall, when we look at this reaction, and I'm just going to zoom in so we can look at these reactions, we can see in the top reaction where we have methanoic acid. So that means that my carboxylic acid is going to be an acid. My NaOH is going to be the base, okay? So the carboxylic acid is going to donate that proton to the OH specifically in my base. So these two combine, and that's where my water comes from. When we have a neutralization reaction, then understand that we are going to make the carboxylate ion. And because I have an oxygen that is negatively charged, the cation of my base is going to sit, okay, next to that negative oxygen, and that's where the salt comes from. So as you can see here, let me just label it. Your acid, oh, I thought it was the highlighter, but it's not. Your acid is your carboxylic acid. Your base is going to be that sodium hydroxide, that lithium hydroxide, that potassium hydroxide. Your salt, your ionic compound, is going to be where specifically your carboxylate salt is paired now with the cation of the base. And lastly, the water, as you can see, is where the OH in the base grabs onto the hydrogen of your carboxylic acid, okay? Now understand that this can happen to any carboxylic acid. And in the bottom example, we have benzoic acid reacting with potassium hydroxide. The salt in the system, okay, which is the carboxylate salt, as you can see, is potassium benzoate. Now, how is this naming different from what we saw in the previous slide? All we have to do is that if you have the cation, as we learned when we were naming inorganic compounds in chapter 6, the name of the cation comes first, and then the second name is going to be the name of the carboxylate, okay? So that's why you see in the top example, sodium methanoate. In the bottom example, we have potassium benzoate. Now, why are these compounds important? Understand that carboxylic acid salts are actually used as preservatives and flavor enhancers. So if you have canned foods at home and you read the food label, you will see that some of them actually utilize sodium benzoate as one of the ingredients. It is known that sodium benzoate is going to inhibit the growth of mold, bacteria, and that's why it's added to fruit juices, to margarine, to relishes, to salads, to jams, canned food. You can see that sodium benzoate, but again, what you're trying to do with the sodium benzoate is to use it as a food preservative. Another food preservative, okay, that it is known is monosodium glutamate, okay, MSG. I don't know who has tried MSG. MSG sometimes is added onto condiments. Now, MSG, which can be added to meat, to fish, to vegetable, to baked goods, it is known that it is going to enhance, okay, the flavor of things. So if you have two dishes, okay, prepared with the same ingredients, okay, same amount of everything, but to your seasoning, you add MSG, okay, in the other dish, you don't have MSG, understand that if you're doing a taste test, the one that has MSG for some reason, and I really don't know the biochemistry of how MSG triggers this enhancement of flavor, but it is known that for some reason the dish that has MSG is going to taste better just because of the properties that MSG has in our taste receptors, okay? Now, there are people that are sensitive to MSG, so that's one of the things that, that you have to be aware of. But when it comes to MSG, understand that this is actually a compound that it is made out of an amino acid. So monosodium glutamate is when actually you take glutamic acid, and that glutamic acid, you actually react it through neutralization to make MSG, okay? That's why sometimes people say, oh, but it is natural. It is, because, you know, you can synthesize it, but it comes from an amino acid, okay? Those are what people claim. Let's now move on to another functional group, which is synthesized from carboxylic acids. And those are esters, okay? Esters are a functional group that is made from the reaction of an alcohol and a carboxylic acid. Let me establish that in order for this reaction to happen, we need acid as a catalyst. Now, where do we find these functional groups? Understand that we can find them in fats and we can find them in oils. And tomorrow, when we talk about chapter 15, we are going to see how these biomolecules that are considered fats, oils, and other biomolecules that we will be discussing tomorrow has this functional group in it. Another place where we see esters is in structures that are related to the aroma and flavor of many fruits. So the image that we have on the left, it's giving you the structure of, this is specifically a fat. And we're going to see what's the difference between fats and oils tomorrow. And you can see that this fat actually has 3 ester bonds in its structure. The image that we have on the right is actually the images for the esters that give rise to the aroma of the following fruits. As you can see, we have the ester for raspberry, the one for pear, banana, orange, peach, pineapple. We have the one for grapes. We have the one from peach. We have the one for apple, okay? When in the fall, when we go back face to face, this is one of my favorite labs. Students actually synthesize these esters, and you are able to do a chemical, what is a physical property test. So you do the reaction, and then after that, after you have synthesized your ester, you will be, or whoever's taking this class is going to be wafting the test tubes and seeing like, oh, this smells like orange. Oh, this smells like banana. Just because we are synthesizing the molecules that gives rise to the different aromas for the fruits, okay? Now, let's go over how do we name esters. As I mentioned a few moments ago, esters are going to be made from an alcohol and a carboxylic acid. So when it comes to the name, we need to visualize that ester and separate it into the components that made the ester. So for example, you can see here that we have an ester. And when it comes to the ester, every time, you guys, this area of the molecule that I'm circling in red came from the alcohol. This area of the molecule here, which is the carbonyl, and whatever the carbonyl is attached to, that comes from the carboxylic acid. And you can see here how the carboxylic acid that we have on the left combined with the alcohol on the right to give rise to the ester that was first introduced to you. Now, when it comes to naming, understand that the first word in our ester name is going to be the name of the substituent in the alcohol. So let me write that down on the notes. So when it comes to ester names, the first word is going to be the substituent at the alcohol. Then the second word is going to be specifically taking that carboxylic acid name, replacing the ic acid with ATE, okay? So let me just write this down. So we're going to take the carboxylic acid name and replace the ic acid ending with ATE. So as you can see, the components that make this ester are specifically ethanoic acid and methanol. So next to the OH, we have a methyl group. So that's where this word comes from. So the methyl group is because of the methanol, or in other words, the methyl alcohol that made the alcohol portion that made this ester. When it comes to the second word, we had ethanoic acid. we remove the ic acid and put ATE. So that's where the word ethanoate comes from. In parentheses, you guys actually have the common name. But when it comes to test time, I'm going to test you on the IUPAC names for esters. Let's actually try a few problems so we can solidify the concept of naming esters. So I'm going to walk you guys through the first example. Okay. So if I create a borderline, meaning let me identify which alcohol combined with which carboxylic acid, that boundary needs to always be between the single bond oxygen and the double bond, the carbon double bonded to oxygen. Okay, it's right there, always. So what does this mean? That in this molecule, this is the alcohol that combined with this carboxylic acid. Okay. What is the name of the alcohol? Let's put it in the chat. What is the name of that alcohol? Two carbon atom on an alcohol. What is that called? Great job, Daniela. This is ethanol. What is the name of the carboxylic acid that we have here? It has 5 carbon atoms. Five carbon atoms on a carboxylic acid. What is that called? Great job, you guys. This is pentanoic acid. Remember, when I'm naming an ester, the first word is going to be the alkyl group that is bonded to the alcohol. So if I have a CH2, CH3 group next to my alcohol, what is the name that I'm going to put as the first word in this ester? What is the name of that substituent next to the alcohol, CH2, CH3? Just put it in the chat. Thank you, Shelley. This is an ethyl, because that's what is attached to my OH. And then my carboxylic acid name, I'm going to specifically remove the ic acid and put ATE. So that means that pentanoic acid becomes pentanoate. I'm going to give you guys 3 minutes to complete the other 2 names for the esters. Let's go over the answer for this molecule. So the carboxylic acid that made this compound is the following. Because remember, we're always going to create that cut or that boundary between the double bond oxygen and the single bond oxygen. Then this carboxylic acid was combined with the following alcohol. To make this compound. So what is the first word in this name? When benzene is a substituent, what is that called? Great job, Gia. This is phenyl. Okay. And then what is the second word in this ester that comes from the carboxylic acid? Remember that we're not going to put the word acid. You take away the word acid, but benzoate is the answer. Great job. So this is not benzoate, sorry. This is butanoic acid. So benzoate, it will be if it's benzene on that corner. This is 1, 2, 3, 4. So the carboxylic acid is butanoic acid. I think benzoate is the next example. Yeah, benzoate is the next example. So out of butanoic acid, the next word is going to be butanoate. Remember that all we're doing here is that we are taking away ic acid and putting ATE. That's where the butanoate comes from. Benzoate is in the next example. Let's explore that one. The carboxylic acid that makes this, again, we cut the molecule right here. This is benzoic acid. So that means that the second word for this one is benzoate. The alcohol in this one is this. 3 carbons as a substituent. What is the name of that? Excellent, that's propyl. And the name of this alcohol is 1-propanol. Okay, so the name of this molecule is propyl benzoate. Questions, naming esters. Let's now look at the esterification reaction, which already we have alluded to because we utilized it in order to name esters. So whenever we're synthesizing esters, as we have discussed so far, this is done through an esterification reaction. The actual scientist that made this reaction, his last name was Fisher. So this is known as the Fisher esterification reaction. As you can see in the Fisher esterification reaction, what we have is a carboxylic acid and an alcohol coming together in the presence of acid and heat to make that ester. In turn, you also form water. As you can see illustrated by the coloring of the bonds, that water comes from the OH of the carboxylic acid combining with the hydrogen in the alcohol, and that's what makes water. Then what happens overall is that specifically the single bond oxygen and the CH3 now are going to make a covalent bond with the carbon in the carbonyl. So that new bond that I was just drawing in, let me just highlight it. This is what this bond is, okay? So that is esterification. Now, when it comes to utilizing esters, at least in biological systems or even in a chemistry lab, we know that esters can actually be cut through the process of hydrolysis. And what hydrolysis is, if we separate the word hydrolysis or lysis, okay, this just means that we're going to quote unquote cut our molecule with water or some portion of a number of atoms that are included in water. Now, when it comes to hydrolysis of esters, it can be done in either one of two conditions. It can be done in acid conditions, or it can be done also on basic conditions. The name out of these two, only base hydrolysis has a specific name, okay? So whenever we say hydrolysis of an ester, in many textbooks is going to, just be related to acid hydrolysis, because base hydrolysis is known as saponification, okay? So let's first discuss what happens to our ester when we put it in the presence of water, acid, and heat, okay? So when this occurs, as you can see in the bottom reaction, if you have an ester, and then it combines with water, acid, and heat, you are going to obtain as a product two things: the carboxylic acid that made that ester and the alcohol. So again, these are the components that made the ester. Through acidic conditions, we are going to regenerate them, okay? This reaction of hydrolysis and water is actually how in our bodies, okay? But we don't need the acid per se, because we actually have biomolecules that are going to ease this process of hydrolysis of using water. But in our bodies, the process of hydrolysis of esters is how the body utilizes, for example, the esters, as we're going to see in the next chapter, the esters that are present in, for example, fats and oils. We can utilize those carboxylic acids in order to generate energy. So the hydrolysis of esters, it is a practice that when you're burning fat in the body, hydrolysis of esters is going to be one of the first steps in order to utilize fat in the body. Now, ester hydrolysis can also happen under basic conditions. And as I mentioned to you guys, base hydrolysis of an ester is also known as saponification, okay? Now, you can see here that when you are saponifying an ester, what you're doing is not technically cutting it with water, but you're using a component that we know is part of the atoms that are in water. Because in the process of saponification, what we have is an ester combining with strong base. And you're going to use heat. What happens in the process of saponification is that now we form a carboxylate salt and we produce the alcohol part of the molecule, okay? So in this week's lab, you guys will be observing and exploring how through the process of saponification is how soap is actually made, okay? So in the lab, there is a discussion about how originally before this more modern era, there was only one type of soap that you will use for everything, for cleaning the house, cleaning dishes, washing your body, washing your hair. Now we have soaps for literally everything. A soap for the dishwasher, something for washing dishes, something for washing our hair, something for washing our skin. So the evolution of soap has been done like greatly. But understand that in general, when soaps are made is through this reaction. You take specifically esters, molecules that have esters. In the case of when we are making soaps, they're going to be fats and oils. You just boil them in base, okay? And that's how you get the soap. Out of the two molecules that we have here, the carboxylate salt and the alcohol, the soap is your carboxylate salt, okay? One of the benefits of having a soap is that we will see specifically in the application in the next chapter, because we're going to explore the reaction, is that when it comes to soaps, creating that carboxylate salt, then now we have an ionic compound. And now that we have an ionic compound, those molecules, since they are ionic, you know, they're going to be soluble in water because you have full ions as part of the structure. So now let's actually go through some problems to determine how to write or predict the products for reactions involving esters. And I put in some of the ones for carboxylic acids here, okay? So let me number these reactions and let's go through them one by one. So far, when it comes to carboxylic acid, we've seen a number of things that carboxylic acids can do. That's what we see in reaction 1 and 2. Reaction 3 and 4 is where we explore what happens with functional groups that are derived from carboxylic acids when they undergo hydrolysis. So when we look at the reaction closely, on reaction number 1, we have a carboxylic acid and we have a strong base. As I mentioned to you guys, when it comes to the exam this weekend, understand that in the predict the products, you guys are not drawing the molecules and submitted them, but you need to be able to identify what is going to be the molecule that it is produced and select what is the correct structure based on the reaction that you guys are doing. So when it comes to carboxylic acid at strong base, immediately in your brain, you have to recognize that this is going to be a neutralization reaction, because I have the carboxylic acid acting as an acid, the strong base acting as a base, okay? The products of a neutralization reaction for a carboxylic acid are the following. We are going to make a carboxylate salt and we're going to make water. And that is always, you guys, those are the two products that you will make in the neutralization of a carboxylic acid, okay? So when we look at the molecule that is given to us, what is the name of the carboxylic acid that I have in this reaction? Let's put it in the chat. What is the name of the carboxylic acid in this reaction? Great job. That is pentanoic acid. So when we write the structure of the carboxylate salt, all we have to do is redraw my pentanoic acid without including the hydrogen. Because in a neutralization reaction, what happened overall is that the OH combined with this H, and that's where my water comes from. So I'm going to redraw my carboxylic acid without including the H. Once that oxygen loses that hydrogen, it becomes negatively charged. Now, I said that this is a carboxylate salt. In order to make it a salt, we need a cation. What is the cation that is going to be paired with our carboxylate? Let's put the symbol in the chat. What is the cation? Great job. K+. So when it comes to naming, remember that this is going to be potassium pentanoate. Let's move on to the second example. Remember that predictive products is all about identifying those functional groups and how they are going to come together to make new functional groups, okay? So in the second example, you guys need to recognize that you are given, and it can be in any order. You can first be given the alcohol and then the carboxylic acid, or like in this case, we have a carboxylic acid and an alcohol, okay? What functional group are we making when we have carboxylic acid plus alcohol in the presence of acid and heat? What functional group are we making? Great, we're making an ester. So when you're looking at the choices, if there's something that is not an ester, you're not going to select it. So understand that in this process, as I mentioned before, the OH in the carboxylic acid is going to combine with the hydrogen in the alcohol. And that's what makes the water in the system. Okay. Next, we are going to write the atoms that I have for the carboxylic acid. As you can see, is 3 carbon atoms. I'm going to link this to the oxygen and put the number of atoms that are next to the oxygen. okay? For those of you that may be confused to the drawing, it is the same thing. If I make that bond pointing up, we have 4 carbon atoms, and through carbon 2 is where the oxygen is bonding. Questions about reaction 2? Let's go over reaction number 3, okay? If you're given an ester and you see that your reagents are acid, water, heat, this is acid hydrolysis. And in acid hydrolysis, we're going to make 2 things. We're going to make a carboxylic acid, and we're going to make an alcohol. How do I know what I'm going to make? I take my ester and I cut it right here. To make the alcohol, I'm going to draw the molecule up to the single bond oxygen. And to make it an alcohol, what's the only thing I'm missing from the structure that I drew to make that an alcohol? Great job. A hydrogen. How do I draw my carboxylic acid? I do double bond oxygen with whatever that is bonded to. What is the only thing missing in this structure to make it a carboxylic acid? So from the structure that I drew, what is the only thing missing to make it a carboxylic acid? Excellent. OH. And you're done. Questions about the acid hydrolysis of an ester? One more hydrolysis reaction. Whenever you have an ester and you have strong base, which it could be lithium hydroxide, sodium hydroxide, potassium hydroxide, any of the 3, and you're heating it, okay? This is what is known as saponification. And in saponification, we are going to create 2 molecules. The first one is a carboxylate salt. The other one is an alcohol. How do I know what are going to be, again, my carboxylate salt and my alcohol in the system? I divide the molecule right here between the carbon double bonded to oxygen and the carbon single bonded to oxygen. The alcohol portion is going to be everything in the molecule up to the single bond oxygen. So when I draw this, I'm going to do single bond oxygen line, okay? As we saw in the previous example, in order for us to make this an alcohol, we need to add a hydrogen, and you're done. That's the alcohol in it. How do I know the carboxylate salt? Remember, in this carboxylate salt, double bond O, the carbon that is there, and this is the rest of the molecule. How do I make it a carboxylate salt? I draw a bond to oxygen, which is negatively charged. And then to make it a salt, I'm going to pair it with the cation in my base. In this case, it is sodium. Okay? So since this carboxylate salt has 4 carbon atoms. What is going to be the name for that carboxylate salt? So in this reaction, what is the product that we formed? Great, that is butanoate. We need to put before the butanoate the name of the cation. Excellent. So this is sodium butanoate. What is the name of the alcohol? A CH3 bonded to OH. What is the name of that alcohol? Remember, that line means CH3. A CH3 bonded to OH. What is that called? That is a methyl group. How do we call a alcohol that has a methyl group? Chapter 12. We got 15 questions from chapter 12. It's not phenol. Phenol is when you have a benzene ring attached to OH. Excellent. This is methanol. The reason why I bring this up, you guys, is because specifically when it comes to chapter 12 and chapter 14, there's a lot of overlap. And there's going to be questions in the exam in which I give you the molecule, I show you the reaction. And just like we saw here in a couple of the examples that I did, the answers that you need to select from are going to be the names of the products. And the name of the products here are within the concepts that we have for this upcoming test. So make sure that nomenclature is something that you are, an expert in that skill. Master the skill of naming. Because again, many of these compounds, we explored how to name them throughout the 4 chapters that we have in this exam, okay? So with that, any questions about reactions of carboxylic acids or hydrolysis of esters? Then let's go on break.